Alright, welcome to section 3.8. We're going to be studying the derivatives of inverse trigonometric functions. Let's get started. Okay, first we have to understand theorem 3. If f of x is differentiable at every point in the interval I, and df dx is never equal to 0 in I, then f of x has an inverse, and f inverse of x is differentiable at every point in the interval f of I. Please take a moment and copy this down. Let me briefly demonstrate what it is that this theorem is saying, in part. We're saying that if there is a function, let's say it looks like this, and there's a point on this function at a comma b, or we can say a comma f of a, it may have a tangent line. Its slope might actually have slope, let's say f prime of a, right? That's what we would label it as, like that. Okay, now if we wanted to have the y equals x line drawn in, we could reflect this and draw in the inverse function. So this would be kind of a cool thing to do. We haven't talked much about inverses this year, right? So what would happen if I drew the inverse function? Well, remember that what happens is all the coordinates trade. So any x-intercepts become y-intercepts. All x values become y values, and vice versa. So this graph, for example, instead of passing through like negative 1 comma 2, we pass through 2 comma negative 1, see? So that point would reflect over to the other side of the red line. This one reflects to here. And this happens for all the points. This is the point 1, 3 right here. But the point 3, 1 would then be on the graph, see? And this point here, which appears to be at like 2, 4, would be at 4, 2, and so on. In other words, the entire curve does this. It's just a rough sketch, okay? And of course the point that we just had would reflect as well. So that point, a comma f of a, would reflect, and its coordinates would literally be f of a comma a. Now the tangent line would also reflect. So the question is, what would the tangent line look like that, right? Let's see if I can draw that one stroke. Something like that. But what would its slope be? So initially this was m equals f of a, f prime of a. This one turns out it's going to have the slope 1 over f prime of a. Now these lines are not parallel, so they don't have equal slope. These lines are not perpendicular, so they do not have opposite reciprocal slopes. What we have here are actually reciprocal slopes. And the basic idea is that x and y have traded roles. Therefore, rise and run have shifted and have become interchanged. Now what the theorem is actually saying is that as long as the first curve, f, is differentiable, and it doesn't have any sharp corners or turns or cusps, sharp turns of any kind, and no horizontal tangents, then the inverse graph, if it exists, will also not have any cusps or corners or sharp turns either. That stands to reason. It won't have any vertical tangents either, so long as f of x had no horizontal tangents. So what we require, remember, for a function to have an inverse in the first place is that it has to be 1 to 1. So f of x must be 1 to 1. And what that means is that it must pass the horizontal line test. So you can see that I carefully chose this function so that it would do that. This guarantees that when we do the reflection, that we will pass the vertical line test and have an actual function. If the function initially does not pass the horizontal line test, then we do not do this. We do not allow for there to be an inverse. We say there is no inverse. Okay, so the rule is the function basically needs to be completely increasing, strictly an increasing function, or it can be a strictly decreasing function, but it cannot have any horizontal tangents, or it makes for this this theorem C would not work, because there would be something non-differentiable on the inverse graph, namely the places of vertical tangency. Okay, for our first example, we're going to let f of x equal x to the fifth plus 6x plus 8. Now we're going to be showing that there is an inverse to this. So first of all, we have to understand that typically when you were taught to do this, you were taught that you needed to take the left side and make it y, right? And then you were supposed to take your x's and y's and trade roles so that it looks like this. Then remember, you were supposed to isolate y so that you could have the inverse. So isolate y to get f inverse of x. Okay, the problem is, quite often you can't really isolate y. I mean, just look at the situation. Y to the fifth plus 6y plus 8. How are you planning to isolate y there? Okay, see the problem? Okay, so what we really just need to do is just make sure that there's an inverse. Doesn't mean we have to find the inverse. So let's look at what we can say here. Since f of x is a polynomial function it has no sharp turns. It also is continuous. In other words, it is continuous and differentiable. And this is because it's a polynomial. It is continuous and differentiable. For all x. Okay, now if we're going to take a look at the inverse function, we need to guarantee one more thing, and that is that in order for the f of x to have an inverse, we need to make sure that it's 1-to-1, because not all polynomial functions are 1-to-1. So I'll write, but is it 1-to-1? Okay, it turns out we can't really tell unless we look at the graph, unless we look at the derivative. Okay, so let's take a look at the derivative. Alright, so note that f prime of x is 5x to the fourth plus 6, which is always positive. Okay, so the idea is we know that if you take x, any value of x, and you take the fourth power, it produces a positive output. Multiplying it by 5 is still positive. Actually, I should say x to the fourth could come out to 0, but multiplying it by 5, we still get something 0 or larger. Adding the 6 on just makes it positive. So I'm going to go through the argument again. We start with any number, we take the fourth power. So far, the smallest number we could possibly have is 0. We then multiply by 5, still the smallest number we could have is 0. Add 6. The range on this is always greater than or equal to 6. So we can clearly say, or safely say, that f prime of x is always positive. Thus, f of x is always increasing and is therefore 1-to-1. Okay, so this argument proves that we have a function, that we have an inverse. Now the question is f inverse, this should say, is f inverse differentiable for all x? Okay, this is a different question, obviously. Okay, in order for it to be differentiable, it cannot have any sharp turns or corners. We've already established that. We've already stated that f of x has no sharp turns and is continuous therefore f inverse of x has no sharp turns and is continuous. Now, does that mean it's differentiable? No, there's always one more little thing, and that's to do with the vertical tangent. Okay. We also know that f prime of x is always positive. So if you go back to part 1, we already argued that. Thus, f of x is strictly increasing and has no horizontal tangents. Therefore, f inverse of x has no vertical tangents. Okay, so having established that there are no vertical tangents, no sharp turns, we can say yes. Our conclusion is that f inverse of x is differentiable. Okay? Alright, now for the tricky part. Find f inverse of 15 and f inverse prime of 15. Okay, we do not have a graph. We do know that there is an inverse. This means that we should be able to find answers to questions like what is f inverse of 15 and what is f inverse prime of 15 and such. Okay, let's say we wanted to find f inverse of 15. So let's write f inverse of 15 equals, let's just give this a name. We'll call it P. Okay, so the question is, what is P? Well, this can also be written as 15 equals f of P. Right? So we're doing the, if you take the f of both sides, then this just cancels out. So basically, like this. Okay, so we can take our original function, f of x, and set it equal to 15. So it would look like this. P to the 5th plus 6p minus 7 equals 15. And then we need to solve it. Oops. Trying to move this down. Anyway, that's a plus. Okay, so how do we solve this? Well, we could use like a synthetic division sort of thing, right? So let's bring everything to one side. Yeah, we're making a mess of this, sorry guys. There we go. Okay, so let's bring the 15 to the left. This was a plus 8, I believe. Sorry, I wrote this function wrong. Divisional problem had a plus 8 here. There we go. Subtract 15 from both sides, and we get p to the 5th plus 6p minus 7 equals 0. And we could use like a synthetic division sort of thing to solve it. Or you could tell that p is 1. Here it's pretty obvious, but one solution here would be that p is equal to 1. So let's solve it. Okay, so let's see. This only divides by 1 and 7. Our leading coefficient divides is only 1. So our only candidates here are 1 and 7, and negative 1 and negative 7. Let's put this in the box. We have p to the 5th, 0p to the 4th, 0p to the 3rd, 0p squared, 6p, and negative 7. And we bring this down. Okay, multiply and add, multiply and add, multiply and add, multiply and add, multiply and add. Okay, so p equals 1 is the answer to that. Okay, so f of 1 equals 15. This means that 1 comma 15 is on the graph of f of x. Okay, therefore, 15 comma 1 is on the graph of the inverse. Right? Because x and y trade. So, what is f of 15? What is f inverse of 15? 1. Okay. The other question we were asked to resolve was what f inverse prime of 15 was. Okay, so to do this, I'm going to try and just picture this real quick. We know that our function initially had a point at 1 comma 15 on it, and the inverse has a point 15 comma 1. We know that the function is strictly increasing, and therefore, looks something like that. I don't know, doesn't matter. And then we know that the inverse function over here would look something like that. Okay, and the curvature right now doesn't matter. We're just trying to figure out basically what's going on. So now what we need are the tangent lines. Okay, so what I'm going to do is I'm going to find f prime at 1, and that should be f inverse prime at 15. Okay, so if I find the slope of this tangent line here, which is f prime of 1, I can then just do the reciprocal and get the slope of this tangent line. Okay, so to find f inverse prime at 15, we will find f prime at 1, and then get this reciprocal. Okay, and it should be very easy to find f prime of 1. It's child's play. So let's do that now. Okay, so f prime of 1 is simply 5p to the 4th plus 6, so that's 11. Therefore, here's the symbol for therefore. F inverse prime at 15 should be 1/11. And there it is. Okay, now for the main topic of the day. So we're going to not spend that long on this. Actually, it's really not very difficult to understand. We're going to be trying to find the derivative of some new functions. So let's just review what we do know. We know that the derivative of sine is trigonometric, it's cosine x. And we know that if we're dealing with derivative of sine, but it's not just x, it's sine of u, where u is some function, then it's going to be cosine of u times du dx. This is the chain rule. Right? Okay. We also have a similar one for cosine, right? The derivative of cosine x is what? Negative sine x. So if we were to take the chain rule perspective and have a function, cosine of a function, it would be negative sine of that function times du dx. And we have one for tangent, which was secant squared. I'll just put in the x one first here, look at the others. Secant squared x, and the chain rule version and we also have them for the cosecant, the secant, and the cotangent. And anything we don't know, we can find through the product rule, quotient rule, chain rule, and so forth. But there are some that we haven't talked about at all, and those are the inverse trig functions. So that's what we're doing now. Okay, so enter the question, how do we find d dx of, and let's just say we're going to do cosine inverse x. Actually, let's do sine inverse first. Okay, so the first thing you have to do maybe is write this as let cosine y equal x. Okay, so what you're really doing is you're trying to look at this statement. I should have written sine. Sorry, I forgot I was going to do the sine one first. There we go. This is the same statement as sine inverse x, right? Okay, so if we wanted to find the derivative, we could just do find dy d dx for both sides. So we'd just find the derivative implicitly of both sides. Here it is, ready? So it's d dx sine y equals d dx x. This side is cosine y times y prime, or you can write dy dx, equals 1. So y prime is equal to 1 over cosine y. Okay, now it'd be nice to have our answer in terms of x, and if we do try to arrange that, we find something very interesting happens. Let's draw a picture of sine y equals x. What does that look like? Let's draw a diagram of that. Okay, well, it means sine y is x over 1. So I guess the angle here is y, the opposite side is x, and the hypotenuse is 1. Interesting. This is the diagram that represents sine y equals x. The Pythagorean theorem gives us the square root of 1 minus x squared for our adjacent side. So this statement here could be written as 1 over, and then cosine y, if you look at the diagram, is adjacent over hypotenuse, which is just square root of 1 minus x squared. Very interesting. The derivative of inverse sine is algebraic. There is no trig in it. So here's our first one. The derivative of inverse sine is 1 over the square root of 1 minus x squared. Okay, and then if you do the inverse cosine, the inverse tan, and the others, they all start to kind of look like this. Yeah, so we'll do a couple more here real quick. We'll speed it up. I don't want this video to go too long. Let's write down the chain rule version of that real quick. So d dx sine inverse of u should be just one over, and then square root of 1 minus u squared times du dx. Or I like to just abbreviate that as u prime over square root of 1 minus u squared. So that's the chain rule version of it. Okay, let's take a look at cosine real quick. Cosine inverse. So what is d dx of cosine inverse of x? Well, we let cosine of y equal x, and we take the derivative of both sides, so we get sine, negative sine y prime equals 1, y prime equals 1 over negative sine y. Our drawing for cosine y equals x is a right triangle, where y is the angle, x is the hypotenuse, and x is the adjacent, and y is the hypotenuse. 1 is the hypotenuse, excuse me. And our opposite this time is the root 1 minus x squared. So when we come back to what we have here, we can write 1 over negative sine y, and sine y is just root 1 minus x squared over 1. Or we could just write 1 root 1 minus x squared. Okay, so you can write your derivative of cosine inverse as an as an algebraic answer as well, and very interesting. This stuff over here. Okay, so the answer to this is negative 1 over the square root of 1 minus x squared. Notice that the only difference between this and the inverse sine's derivative is the negative. Very interesting. And the chain rule version of that, of course, would be dx of inverse cosine of u equals, and then we just need a negative u prime over the square root of 1 minus u squared. I'll leave it to you to try tangent, secant, cosecant, cotangent on your own time. I will give you the answer to the tangent though. So it turns out, you'll have to draw your own diagram for this. We'll bring it to class. The derivative of inverse tangent is cos 1 over 1 plus x squared. And notice that there is no square root. Interesting. And the chain rule for that is u prime over 1 plus u prime squared. I'm sorry, over u squared.